Business Mathematics 1, How to Calculate the Eigenvalues and Eigensubspaces of an Endomorphism in R3. This video consists of the next sections. 1. Problem statement. 2. What do you need to know to solve this exercise? 3. Solution. 4. Summary. 5. Proposed exercise. Problem statement. Consider f of R3 to R3 the endomorphism in R3 with the analytical expression f of x, y, and z equals 4x plus 3y plus 2z, 2y, minus x minus 3y plus z. You are asked to 1. Calculate the matrix of f in the canonical basis of R3. Calculate the characteristic polynomial of f. 3. Calculate the eigenvalues of f. 4. Calculate the eigensubspaces of each eigenvalue. 5. Calculate a basis in each eigensubspace. 6. Calculate, if possible, a diagonal matrix associated to f. What you need to know to solve this exercise. What is a canonical basis in R3? How to calculate the matrix associated to an endomorphism. How is the characteristic polynomial of an endomorphism defined? How to calculate determinants of size 3. How to calculate a polynomial's roots. How is an eigensubspace defined? How to solve an equation system with 3 linear equations and 3 variables. And how to study when an endomorphism is diagonalizable. 1. Calculate the matrix of F. The matrix of F is formed by the images of the canonical basis in R3. The image of the first vector is f of 1, 0, and 0 equals 4 times 1 plus 3 times 0 plus 2 times 0, 2 times 0, and minus 1 minus 3 times 0 plus 0, which is 4, 0, and minus 1. The image of the second vector is f of 0, 1, and 0 equals 4 times 0 plus 3 times 1 plus 2 times 0, 2 times 1, and minus 0, minus 3 times 1, plus 0, which gives a total of 3, 2, and minus 3. The image of the third vector is f of 0, 0, and 1 equals 4 times 0, plus 3 times 0, plus 2 times 1, plus 2 times 0, minus 0, minus 3 times 0, plus 1, which is 2, 0, and 1. So the matrix associated to F in the canonical basis of R is, by columns, F equals 4, 0, minus 1, 3, 2, minus 3, and 2, 0, 1. 2. Calculate the characteristic polynomial of F. The characteristic polynomial of F, which we denote by P of lambda, is the determinant of the matrix M of F minus lambda times I, where MF is the matrix of F, lambda is the polynomial's variable, and I is the identity matrix in R3. So first we calculate M of S minus lambda times I. M of S minus lambda times I by columns 4, 0, minus 1, 3, 2, minus 3, 2, 0, 1, minus lambda times 1, 0, 0, 0, 1, 0, 0, 0, 1. Which equals 4 minus lambda, 0, minus 1, 3, 2 minus lambda, minus 3, 2, 0, 1 minus lambda. Then P of lambda is the determinant of the previous matrix. P of lambda equals M of F minus lambda times I by columns 4, 0, minus 1, 3, 2 minus 3, 2, 0, 1 equals 4 minus lambda times 2 minus lambda times 1 minus lambda plus 2 times 2 minus lambda equals 2 minus lambda times lambda squared minus 5 lambda plus 6. So the characteristic polynomial is P of lambda equals 2 minus lambda times lambda squared minus 5 lambda plus 6. Three. Calculate the eigenvalues of f. The eigenvalues of f are the roots of the characteristic polynomial P of lambda equals 2 minus lambda times lambda squared minus 5 lambda plus 6. By doing 2 minus lambda equals 0 and lambda squared minus 5 lambda plus 6 equals 0, we obtain that the eigenvalues of f are lambda 1 equals 2 with multiplicity 2 and lambda 2 equals 3 with multiplicity 2. 4. Calculate the eigensubspaces. The eigensubspace of the eigenvalue lambda 1 equals 2 is defined as h of 2 equals x, y and z submitted in R3, f of x, y and z equals 2x, y, z. Therefore, we must solve the equation system 4x plus 3y plus 2z equals 2x, 2y equals 2y, minus x minus 3y plus z equals 2z. The second equation is trivial. If we clear, for example, x in the third equation, we have x equals minus 3y minus z. Now we substitute in the first equation and get y equals 0. And replacing this value in x, we have the equation x equals minus z. Therefore, h of 2 equals x, y, z in R3, y equals 0, x equals minus z. Now we repeat the process to calculate eigensubspace of eigenvalue lambda 2 equals 3. h of 3 equals x, y and z in R3, f of x, y and z equals 3x, y, z. We must solve the equation system 4x plus 3y plus 2z equals 3x, 2y equals 3y, minus x minus 3y plus z equals 3z. From the second equation we get y equals 0. Substituting in the third one we get x equals minus 2z. And replacing both results in the first equation we get a trivial result. Therefore, h of 3 in x, y and z in R3 is y equals 0, x equals minus 2z. 5. Calculate a basis in each eigensubspace. The dimension of any vector subspace S is dimension of S equals number of variables minus the number of equations. As h2 equals x, y and z in R3, y equals 0, x minus z, its dimension is dimension of h in 2 equals 3 minus 2 equals 1. Then we just need one vector for a basis in h2. So we choose a vector verifying the equations of h in 2. For example, u1 equals minus 1, 0 and 1. Vector u equals minus 1, 0, 1 is a basis in h2. Now, as h3 equals x, y, z in R3 is y equals 0, x equals minus 2z, its dimension is dimension h2 is 3 minus 2 equals 1. We need one vector for a basis in h3, so we choose a vector verifying the equations of h3. For example, u1 equals minus 2, 0, 1. Therefore, vector u2 equals minus 2, 0, 1 is a basis in h3. 6. Calculate a diagonal matrix associated to F. First, we must check if F is diagonalizable or not. For that, we must study if the dimension of each eigensubspace coincides with the multiplicity of the eigenvalue. We know that the eigenvalues with multiplicity 1 always verify that equality, so we only need to check if for the eigenvalue lambda 2 is 3. As we saw before, the dimension of h in 3 is 1, but the multiplicity of lambda 2 equals 3 is 2, so the dimension h in 3 isn't the same as m of the multiplicity 3. Then F is not diagonalizable, which means there isn't any diagonal matrix associated to F. 4. Important conclusions. The matrix associated to an endomorphism is calculated writing the images of the vectors in the canonical basis into columns. The eigenvalues of an endomorphism are calculated as the roots of the characteristical polynomial. The eigensubspaces of an eigenvalue is the set of all vectors verifying f of u equals lambda times u, and when solving the equation system for an eigensubspace we will always find at least one trivial equation. The dimension of an eigensubspace is always less or equal than the eigenvalue's multiplicity. To be diagonalizable, an endomorphism must verify the dimension of h of lambda equals the multiplicity of lambda for all its eigenvalues lambda. We don't need to check the equality for eigenvalues with multiplicity 1, because all of them verify it. To be able to calculate a diagonal matrix associated to an endomorphism, the endomorphism must be diagonalizable. If it isn't, there doesn't exist any diagonal matrix for it. 6. Proposed exercise. Consider f of R3 to R3 the endomorphism in R3 with analytical expression f of x, y and z equals minus x, minus 2y plus z, and y minus 2z. You are asked to 1. Calculate the matrix of f in the canonical basis of R3. 2. Calculate the characteristic polynomial of f. 3. Calculate the eigenvalues of f. 4. Calculate the eigensubspace of each eigenvalue. 5. Calculate a basis in each eigensubspace. 6. Calculate, if possible, a diagonal matrix associated to f. This video was created by Belén Corbacho in collaboration with Hannah Lovegrove in 2012.